Bismillahirrahmanirrahim. Allahumma salli ala Sayyidina Muhammad wa ala alihi wa barik wasallam. We'll talk in this video about machine learning from a practical perspective. We'll not go into the theoretical details. We just touch briefly on the terminology for AI, machine learning, and deep learning, a slight difference in these terms, and then we'll try to implement a machine learning problem in Python. And for the details, we'll try to make other videos, but for now, this video will just touch on the surface and try to demystify the myth around machine learning. So, first of all, what's artificial intelligence? It's just a broad term. It refers to all the tasks which were traditionally thought to be done by humans only, and computers weren't capable of doing such intelligent tasks, and developing software to do such complex tasks is considered as AI. But it has many subdomains. It's just a broad term for all these software, and the most important and the core area in artificial intelligence is machine learning. Machine learning basically refers to the process by which a software learns by itself how to do a task. So to reiterate, machine learning is specifically machine learning refers to all those techniques by which a software learns by itself how to do certain tasks. So it sounds a bit confusing, but actually the problem is that we can't program software for every task, because there are a lot of tasks, especially the complex tasks, which humans do. Because why? Because first of all, during these complex situations, there can be unseen problems which we can't foresee beforehand, and hence we can't program a software for them. Secondly, the more important factor is that there are a lot of tasks we do, still we don't know how we do them. So how we do them is still not well understood by humans. So we can't program, of course, something we don't know how it's done. So, but still our brain does that. The problem is we know how to do those things. Our brain knows, but we don't know the method, the mechanism by which we do these tasks. So the best example is the speech recognition and the auto driving. So we'll touch both of them briefly. For example, auto driving, while driving, the humans are doing a lot of thinking, a lot of computations in parallel, and we don't realize that. But we judge the distance of different objects, we calculate their speeds, we consider the weather, we consider the braking distances, and there is a lot of there is a large view in front of our eyes, and we have the idea of the surroundings as well. So it's quite a lot of decisions going on. So but if we have to program an auto driving car, we can't easily write down set of instructions for all these tasks, right? So what is the solution? It's machine learning. How it's the machine learning learns it, we'll touch on that later. Secondly, the speech recognition. Speech, what if you think of speech, it's just changing air pressure hitting our ear. This if you consider the speech signal, acoustic signal, it's just different air pressures hitting a eardrum, and from that we make sense, we recognize the words, the meaning, the context, the emotions, the sentiment. We get a lot of information from these changing air pressures. So still we don't know how that's done. Those decisions, those inferences are made in our mind. So of course it's not easy for us to write down a set of instructions for a program to understand speech. Hence the solution is machine learning. Again, we'll just briefly discuss how the machine learning is able to learn these things. So then there is another last example for intelligent tasks like sentiment analysis. For example, the companies and the political parties use Twitter and social media data to judge the public response to certain issues. So for that, they judge the sentiment in the tweets, and they analyze statistically what percentage of people have a positive opinion about something. So for that, it's not easy to program as well, because it's not based purely on words. The same words mean different sentiment in different context, and the language is quite a complex issue. For example, if someone prevents trouble, he's good, but if someone puts people in trouble, it's not good, right? So these are two examples of such tasks which are quite complex to judge. Yeah. So the machine learning, basically, now what's machine learning? Machine learning is basically the process to learn how to do these tasks, right? And one of the methods, the particular methods, is deep learning, which is one of the machine learning methods. So because this is the most famous one, so we'll focus on this one only. Basically, all the machine learning methods use data sets to learn how to do tasks. And this is one technique to learn using the data set. So this technique is deep learning. What's that? Basically, it's based on neural networks. What's neural network? It uses some input, maps that into numbers, and then translates that input to an output via mathematical transform function. What's that function? It's just linear sum of the inputs. Using a data, the neural network learns these weights, this 2, 0, 0, 1, so that the arbitrary function is tuned to map the input and output, right? So by learning these weights, this neural network is trained on a labeled data set to learn a function that maps input to output. So it's we won't go in the detailed maths, as I said, but it's the general framework. This is an example of how it learns, because for example, this is a function mapping to x and y input features to an output. So the network learns this minima point, which is the minima for error. That is, this is the error for the between the desired output and the computed output for these features. So the function of these using these weights should give a least error. So eventually these weights are tuned to reach this point. So anyways, this is a very simple neural network, but for complex tasks, we have to map some input to the output. For example, the speech waveform to the corresponding word of language. It's not that easy to map with small architecture. So we keep stacking these neural networks on top of each other, which is the function. We get a function of functions, so to get a complex mapping. So this function of functions is called deep network because of its depth, because of stacking of neural networks. So that's where the word deep comes from, and that's why it's called deep learning. So how these, now we'll just look at implementation details. So basically the idea is that we need a numerical input and numerical output to learn a mapping function. What are the numerical input and outputs? They are different for different tasks. So for every task, we have to translate the input to a numerical number, a numerical vector, and same for the output we have. So first, let's see how we translate the input features. For example, these are two examples for text. There are a lot of techniques, but the simplest and the most famous one is the term frequency based. For example, if in a sentence, first of all, we create an array of size which is equal to the vocabulary size of a total text data set. So in this text data set, these are different sentences, and for each for all of those sentences, the total number of unique words is 1, 2, 3, 4, 5. So these are the total words in this data set, and for each sentence, we indicate how many times a particular words from this vocabulary appears. So for good movie, good appears once, movie once, so rest are represented by 0, good and movie by 1, 1. If a word had appeared multiple times, then that index in this vector would have had that value higher than 1. So this is a numerical representation for text data. Similarly, for images, images, are made up of pixels, right? That's where our cameras are, that's how our cameras are rated, megapixels and all that. So image is made up of small picture cells, the pixels. So, and then each pixel has intensity value for one of these colors, red, green, blue, and every color can be made up of these basic colors.
So what's the picture? Picture is the color intensity values of RGB for each pixel, right? So it's just already a numeric matrix, which is number of pixels in both dimensions across 3, with the 3 represents the colors. And these were the input representations. And now let's go to the output for this neural network. So this output should be different for different tasks. For example, if it's a classification task, that is to classify which sentiment this sentence represents, or to classify if this image is a cat or a dog. So for such tasks, the output is, the classification tasks output is a one hot encoding vector. What's one hot encoding vector? It's just a vector with dimensions equal to the number of categories in the data set. And for each sample, the category which represents its category, the dimension which it represents its category is turned to 1, rest are turned to 0. So for example, in the data set, we have 4 samples and totally 3 classes, red, blue, green. So our output vector for each sample will have 3 dimensions corresponding to one class, red, blue, green. And for each vector, the class it represents will have a value 1 in its respective index, and the rest will have 0. So it's just 1, 0, zeros. And the neural network will now try to map these input features from here to this 1, 0, 0 vector at output. And eventually it will find some weights which are optimal for this. And after training on labeled data, on unlabeled data, we will get the predictions. We'll train on training. So that's almost it. Let's now try to implement it in Python. So for that, I have used a very simple example of image classification, binary image classification. So we have, as I said, a training data set with labels, which is like, we'll use its labels as well. So it's zeros and ones, just a binary classification, images of 0 and 1. So we have to predict if the image is 0 or 1. We'll use this training data set to tune our model, and then we'll use this test data set to test our model, which is also a lot of images, like 2115 images will be used to test the model, and we'll tune it on these 12665. So for these images, we have the CSV files with the image names and their corresponding labels. So here in this file, the training for training data set, these labels we'll use. So this one contains the image name and its corresponding label if it represents 0 or 1. So that's it. So let's start. These are the required libraries. The PIL is inbuilt Python library for images, and TensorFlow, you know, it's the most famous deep learning library for deep learning library, and mostly it's used to implement besides torch. And so first we'll import these libraries. This matplotlib, it's used for visualization, the plotting, and NumPy is of course for numerical computations. So first we'll go to this directory where we have this training and test sets, and we'll import the images. But before that, we'll go to this parent directory where we have these CSV files. So for training and test, to import the names of the images, to then consequently we import those. So here I just took, let's see, first we import the CSV files in this DSP_label. What's this shape of this CSV file? The shape is 12665 cross 2. This is for our training CSV, right? Because the samples are 12665 and each sample has 2 entries. One is the label and other is the image name. So now we use these values. For example, from DSP_label, we use first sample, the 0th index, and for that sample, the second index, like this 0.png. So we go to the 0.png and open it, import it using PIL. Yeah. So we imported the path. We append the training folder path, and then we import it, and then we display it with matplotlib. So the first image is this one, and now if you see its shape, it's actually grayscale, not colored image, so it will not have RGB values. It will just have the dimensions. So 28 across x-axis, 28 across y, small image. So we have this, and then we flatten it to feed a simple feed-forward neural network. We can use RNN and CNN for 2-dimensional data, but right now we just use a simple feed-forward. For that, we need single-dimensional inputs, so single axis inputs. So we just flatten each input. This was one example. Now we import all of the data set. I already imported this because it takes a little bit of time. So okay, now again imported it. Anyways, so this is yeah, what this does is this passes the CSV file for training and test to this function, and this function read goes to every entry in this CSV file. First imports its label, then its name, image name. From the labels we return this label list for the data set, and from images we return this input images which we import using PIL. So this is just our data set shape. We import for training in, training out. Training in is images, training out is training labels, and for test in is to test the images to test, and this we will just use to reserve to test our model. So the training in data set, because we have flattened every image, so our training data set is the number of samples cross features, which is flattened image. Labels are just the one-dimensional 0, 1, and similarly for test it's less samples, but it's the same axis on the same dimensions for the other axis. So now this is our model, neural network model. Because it's a simple task, so we just use single layer model, right? So one input layer, which has the units equal to 784, the number of dimensions for each sample, and then we connect it directly to the output layer, which predicts the class. Since the target task is binary classification, so we only have one output, which will predict either 0 for image 0, 1 for image 1. So we don't need, if it for multiple classes, then we would have had one hot encoder. So that's it. Now we train the model. For training, we use optimization function ADAM, which is a method to optimize our function, which uses different techniques to find the optimal parameters quickly. It's basically based on gradient descent, which uses the error differentiation with respect to parameters, but we'll not go into the mathematical details. And the loss we have to minimize is the difference between target category and predicted category. So we'll train and we'll check, we'll reserve a data set to check the accuracy after each iteration. And when the 20% of data set we reserve, and when the accuracy will decrease, will not decrease for 4 iterations, the model will stop training. And we save the training history, the accuracies, the loss in the this dictionary. So loss is just opposite to accuracy. So you see after 4 turns it stopped decreasing, so it's already optimized. Now we plot the history of this training loss for reserved validation set, as well as for the set we use for training. So here I just actually try to skip the first 5 values of this, but there are only 6 values. The 6 iterations of training, these are the 6 iterations. So from the plot starts from 0. So it's the loss was 0.7, which is the difference between the computed output and the target output, which is the category in each iteration. So after the 7th iteration, our model was already almost had a very small error on training set. Now let's see how it will perform in the test set. For test set, we predict this. For this, we trained our model using fit, try to fit the model on training data set, and passed it the training inputs and the labels, and the images and the labels. So now we predict it using the test set, and test set is the images of test data set, and then we'll check if the predictions are equal to the actual labels which we imported from the CSV file, and then we'll calculate the accuracy from that, and we see it's 99.4%. So our model is very well optimized very quickly, because it was a pretty simple task. So you see it just took 5 iterations to get to 99.4% accuracy. So this was end-to-end task for image classification, and just the pipeline is the same, just we'll have to add layers for some complex tasks, and the output categories will be more than 1. And but the main idea of any machine learning program, the end-to-end pipeline will be of the same structure. So that's it for the basic intro. Thanks for watching. So inshallah, we'll try to cover in detail some specific machine learning topics in later videos. So let me stop this recording.